All right. Hello, everybody. My name is Martin. I am a senior research engineer at QuantStamp, and I will be talking about randomness on chain. Uh, Before we hop into the talk, I just want to point out that QuantStamp is actually sponsoring a bounty at this hackathon. So if you're hacking, please do listen to the talk. You might find some useful information in here. Thank you very much. All right. So our bounty is about randomness. We are asking that you develop an app that uses randomness on chain in a non-trivial way, so that this randomness is not exploitable. There is a QR code that leads to a blog post about what you should be doing with randomness, and on the official Ether website you can find the write-up for the bounty as well. So let's go to the technical section of the talk. If you have ever developed in any programming language other than Solidity, you would probably know that the language provides you with a function called random or something similar that generates random numbers. Solidity doesn't have it. And the reason why it doesn't have it is very simple. It's because we have a bunch of Ethereum miners. Every single miner is maintaining the state of the blockchain on their local environment, and they have to be replaying transactions to update the state. And if there was some opportunity for them to generate some random numbers, various miners would be arriving to varying results, and there would be no integrity of the state guaranteed. So therefore, a primitive for generating randomness doesn't exist. However, we want it, right? Because we want to develop lotteries, we want to develop NFT drops and decide who should be getting which NFT, and we want to develop games. So therefore, the developers went out of their way to devise various techniques of how to get some randomness on chain. So these techniques include some deterministic computations based on blockchain data, maybe block hashes or something similar. They use something that we call a verifiable random function that you can implement yourself, or you can use some existing implementation. There is one provided by Chainlink. It includes a commit and reveal scheme, which I will be talking about. It's a design pattern. And we can also use something that I'm calling a trusted randomness provider. It would be a trusted agent that will just generate random data off-chain and send them on-chain. But this is the part that I will not be discussing because this is not really decentralized. So all these techniques can actually work if you use them correctly, and all of them can fail if you use them wrong. And this is what the talk will be about. So before I jump into the recent times, I want to backtrack into 2018 and demonstrate to you what can go wrong with randomness on-chain. So in 2018, we had some application. It was a Ponzi scheme called Fomo 3D on Ethereum. It was extremely popular. And what Fomo 3D wanted the users to do was to buy in with some amount of Ether, buy some kind of thing called a key. And while buying the key, the Fomo 3D application would roll a random number, and it would decide, or it would make a random decision, and it would decide whether the user is lucky, and if they were lucky, it would send them some amount of assets. It would be like an airdrop type thing. So here I have a heavy simplification of the code that was present in there. I have a method that is called enter. It's external, payable, and on the first line, it checks that I'm providing or calling this method with the right amount of money. So let's say 1 Ether. And then it will take the current block hash. It will take it mod 50. So it gives me some 2% probability that I will be lucky. And if I'm lucky, it will send me 1% of the balance of the contract. So that was roughly what happened in Fomo. This is very clearly exploitable, so I can construct a smart contract which will be looking somewhat like this. It will implement a function which will, on the very first line, check that the block hash mod 50 is 0, and if that holds, then it will buy into Fomo, otherwise it will not. So such a function and such a smart contract would be buying into Fomo, knowing that 100% sure it will be rewarded with an airdrop. So this would be the exploit. And clearly, the developers of Fomo 3D knew about it, because what they included in their smart contract was a line that required that the size of the bytecode associated with the caller of this method would be 0. We are assuming that smart contracts would have some bytecode on-chain, right? So that was the protection that they chose to use. And it was actually wrong, because we know that there are several moments in the life cycle of a smart contract when it still doesn't have any code on chain. One of them being the moment of construction. So I could still exploit it in the very same way by moving the exploit code into a constructor of my smart contract exploit. It would do the same thing, check that the block hash mod50 is 0, and it would buy into Fomo only if it is mod50 0. So this didn't work. The proper way of making sure that smart contracts cannot interact with your own contract is the following. You would be requiring that the message sender is the transaction origin, because we know that smart contracts can never initiate transactions themselves, so they will never be the transaction origin. I have to step aside here for a second. There is a well-known post on Stack Overflow by Vitalik, which says that developers should never assume that transaction origin will remain useful or meaningful. But for the purposes of this talk, it still exists, it is useful and meaningful, so this is right now a valid way of protecting your smart contract from being interacted with by other smart contracts. So presumably, this should be working as a valid protection. But it doesn't, because it's 2022, and now we have a project that is called Flashbots. So let's talk about Flashbots and how we can use them to exploit many things, including randomness. So Flashbots is a service that provides people with a private mempool into which you can send transactions. And Flashbots will give you some guarantees about how these transactions will be mined. So specifically, you can send in batches of transactions, and Flashbots will guarantee that if they succeed in mining a block with those transactions, these transactions in the batch will be sorted in the block consecutively without any transaction coming in between. And they will also guarantee to you that all the transactions in the batch will succeed. Otherwise, they will not be projected on-chain. So you can use this to exploit things. Again, I don't want to be stuck in 2018, so I'm fast-forwarding into 2021, I guess, and I want to be talking about a smart contract that is a little bit more recent, but still exploitable. So in 2021, at the end of the year, what the developers released was this interesting game that featured some NFTs. They were wizards, and there were some dragons. And somewhere in the game, you would have the opportunity to stake your NFTs to collect some in-game assets. Those NFTs would be collecting the in-game assets, and eventually you could choose to unstake those NFTs and get your in-game assets. They call them GP. They were the GP tokens. It was an ERC20 token. So you would unstake the NFTs, and you would presumably get back your GP tokens. However, somewhere in the unstaking process, the developers wanted to make a random decision whether you will actually receive your GPs or whether they will be taken away from you and paid to the other participants of the game. So the method, this is actually an exact excerpt from Etherscan that I have taken. So the method for unstaking is called claim many from tower and flight. It is the external method, and you can see that the developers here were also very aware that smart contracts can cause some real mess, so they wanted to prevent interaction of smart contracts with this method, and therefore they included the requirement that transaction origin is the message sender, right? And then this method iterates over all the staked NFTs of the particular caller, and it will calculate how many GPs those NFTs collected. That's what we are maintaining in this variable ode. And if that number is not 0, then it will mint the GPs to the particular user. The number of GPs that are being collected and they should be minted to the user is calculated in the subroutine. So I'm going to switch the slide to show the subroutine. And particularly in this subroutine, I am interested in this highlighted part where if we are unstaking, they have some component called Randomizer that is supposed to generate a random number. Then they take that random number, they take a bitwise end with 1 and make sure that the result is 1. So they are actually checking here that this number is odd. And if the number is odd, they will say, no, we don't owe you anything. All the GPs that you have collected will be taken away from you and they will be paid as tax somewhere else. Right? So this is the mechanic how it worked, and again, this is exploitable using Flashbots. Because what you can do, you can construct a transaction batch that looks as follows. In the first transaction, you will unstake your NFT During that unstaking, something will happen, and presumably you should be getting your GPs, right? So in the second transaction, you can actually assume that you yielded the favorable outcome, that you have collected the GPs, and they are currently in your account, so you can try to use them. You can try to take them and transfer them somewhere else. Or you can try to transfer them to yourself. It doesn't really matter, but you will use them. If you have them, the second transaction would mine without an error. If you do not have them, so they were stolen and paid as a tax somewhere else, then the second transaction would be failing because you're trying to use tokens that you do not own. So if you send such a batch to Flashbots, because they guarantee that this will be mined only if both the transaction pass, you will have the guarantee that if these transactions mine, you actually did collect your GPs. And if you did not collect your GPs, then you can just try again, and try again, and try again, and try again, because not including these transactions on-chain will not cost you anything. You don't even have to pay gas, right? There's no transaction that failed on-chain. So this game mechanic was actually broken from the very beginning, and all the people playing this game didn't have to pay any kind of taxes or GPs or anything like that. So this is how you would be using Flashbots to exploit randomness that resolves immediately. The second thing that I want to talk about, it's a different technique for producing randomness, is the commit and reveal scheme. So commit and reveal is a design pattern. It breaks the production of randomness and its resolution into two steps. In the first step, the user has to commit to some action so that they cannot retract their commitment later. It's done, and at some point it will be resolved. And so that they cannot infer the outcome of the commitment while they are committing. And for some technical reasons, we also usually want that they cannot recommit and resolve the same action again. And the point is that the outcome will be decided sometimes later during an event that we call reveal. So here is an example how such a code could look and is actually wrong. So I will explain both. First of all, I have the two functions that I was referring to. I have commit and I have reveal. During commit, the user comes and we are checking that they do not have an existing commitment yet. And if they do not have an existing commitment yet, what we will do is we will generate a random number using a black box function that I am here calling getSafeRandom. The implementation of this function is something that we do not care about in this talk, but we are assuming that it's absolutely safe, not manipulable, not predictable. It's actually just okay. And we will take this random number and we will put it in the mapping commits associated with the caller. And then in the second step, in the reveal, that would be called by the same message sender, we check that the message sender has a previous commitment. And then we will take that random number from that commitment, we will take it mod to, and if the user is lucky, so that number is even, then we will send them the balance of the smart contract. So this would be an example of a commit and reveal that is unfortunately coded wrong because it violates the assumption that users can know nothing about their commitment at the time of when they are committing. The reason why they actually infer all the information they need in here is that this mapping is public. Right? Because I can, again, construct a smart contract which has this function that commits, and then it queries the commitment in the mapping of commits and checks that it is actually even. And if it is not, then it will revert the transaction and nobody committed to anything. So this is actually wrong. And this also leads us to a suggestion how we should fix it, right? We should make it private so that this mapping cannot be queried by other smart contracts. So this would now appear fixed, but again, it is not fixed because we have Flashbots. Flashbots would be able to exploit this exactly the same way how I have described previously. So we would first commit in the batch of transactions, then immediately after we would reveal. That would be a different transaction, and we would assume that we were lucky that this commit and reveal combination actually yielded the reward, that we received some ether in our address and we would try to use it. If it did, the transaction batch mines. If it did not, the transaction batch doesn't mine, it doesn't cost me any ether, anything, and I can just try again. So what we would need to do to fix this is to ensure that Flashbots cannot organize the transaction batch to a single block the way how they usually want to do it, right? So we would need some block locking mechanism. So to fix that, I have here introduced another mapping of blocks. And during the commitment, which looks very similar to what you have seen before, I'm recording the number of the block when the user is committing to the action. And then during reveal, I'm checking that the commitment happened at least 32 blocks in the past. And if it did not, the user just has to wait a little bit longer and then can reveal later. So this will prevent the Flashbot's engine from taking the batch of transactions and putting them consecutively in a single block, right? Because this will just never pass through this requirement. This number 32 in here, that's a very arbitrary number. I just chose 32. The point is that you would want to choose a number that is high enough so that Flashbots cannot guarantee or reasonably assume that they would be able to mine so many blocks consecutively themselves as the single miner, right? Because if you imagine that Flashbots were able to acquire sufficient hash power in the network so that they have a solid chance of mining, let's say, 2 consecutive blocks, and you only enforce that the commit happened in the past block, then sometimes in the future this might become exploitable again. So here we are making a bet that Flashbots in the near future, or for the time of the relevance of this game, or a smart contract, will not be able to mine 32 consecutive blocks, which sounds like a fairly safe assumption. However, I have broken this code in a different way, which is also something that I have seen in projects that we were auditing at QuantStamp. So here what I have done is I have taken the block hash of the time when I am calling the reveal, and I am actually taking it modulo of that commit, right? And that's this variable mod. And then I am taking the result and taking a mod 2. If that is even, I will be rewarding the user. So the effect of this is that the outcome of the commit depends on the block that the commit, the reveal is being called from, right? So if I call reveal in different blocks or varying blocks, I will be coming up with varying results. And again, that is wrong because I can attack it. I can commit myself using a regular transaction, but that commitment, it just means that at some point I will be revealing, but everything will be decided like way later during that reveal. So I can again use Flashbots to attack the reveal mechanic. Using 2 transactions, I will be calling reveal, assume favorable outcome, and then try to use my reward. And I will be trying over and over, and because reveal produces different results, at some point I would succeed. So the proper way of fixing the code would be not breaking it again, but introduce these 2 mappings and waiting sufficient number of blocks so that the outcome of the reveal is every single time consistent. I wanted to talk about the verifiable random function, but I see that I'm slowly running out of time, so I am just going to skip it. But what I'm going to do is conclude the talk and tell you what you should be doing. So your question right now should be, what the hell should I use in my application for producing randomness? And the answer is clear. It really depends on what that application really is. So if you are developing an application that is going to be relevant in a very limited time frame, say that you are developing an NFT drop and you are assuming that the drop will be so popular that it will mine within the next 3 or 4 blocks, right? In such a case, honestly, anything will do, because the users, to be able to exploit any kind of randomness, have to have the opportunity to try over and over. If you are developing something where the user will be lucky when they manage to push through a single transaction, then there is no cherry picking of the results. They will be lucky if they manage to push a single thing through, right? So in such a case, it doesn't really matter. On the other hand, if you are going to produce something that has a long time frame, it's going to be some lottery where users can bet repeatedly or something like that, or a game, then you probably want to use the commit and reveal scheme. And if I was able to cover the chain links VRF, I would actually be able to explain to you that the asynchronous provision of randomness that Chainlink allows is just a very special case of the commit and reveal scheme. So this is your answer. With that, I have a very short time for questions, so please feel free to have questions. I just want to point out QuantStamp actually has a booth on the lower floor, so feel free to pop by. We are hiring, so if you like to dig into smart contracts and figure out how to exploit them, we would very much like to talk to you. And yeah, questions, please. I don't see any. So thank you, and next speaker.